So how are the fortunes and potential survival of little sea turtle hatchlings related to probably the most famous and gifted physicist that's ever lived? I'm a volunteer for the Loggerhead Marine Center, which works with the Florida Wildlife Commission to monitor a 9.5-mile portion of the beach off of the city of Juneau. And every year, thousands and thousands of sea turtles come up on that beach to make nests. Every morning when the researchers get up, they monitor that beast, they look at the tracks, follow them up to the nest, and then every single nest is cataloged with a date and a GPS location. That way they can monitor the nest, and then they can go back and watch the nest about 2 months later to make sure that it's hatched properly, and if there's anybody has been messing with the nest. So GPS is very important. Also, when turtles are rehabilitated and released, many of the turtles are equipped with GPS trackers so they can monitor the turtle to see if it's acting normally or if it's going back to the natural behavior that they would expect when it's released. So, now we're going to talk about GPS. GPS stands for the Global Positioning System. That's the system that lets you anywhere in the world pull out your phone and find out exactly where you're at. And it has been around probably 25 years and commonplace, but this is how GPS works, very simply. Visualize that you have two satellites at a wide distance apart in space, and that they send microwave signals back and forth to each other, and imagine that it takes exactly 1/10 of a second for the microwave signal to get between those two satellites. Since we know that microwaves travel at the speed of light, which is 186,862 miles per hour, you can calculate the distance between those two satellites. Now, visualize that simultaneously, they are also sending signals to a ground station where you know the exact location. So that allows the other two distances to be calculated. And if you have those three distances and the calculations, you can use simple geometry to find out exactly where those two satellites are in relationship to the ground station. So this is very simple, right? It's in 2 dimensions, but the real world is in 3 dimensions. But I wanted to just show you how the calculations are done. But to make the GPS system work in 3 dimensions requires a constellation of at least 24 satellites rotating around the Earth at all times. Now, these types of calculations are going on between the satellites and between the ground stations, and at every single moment, you know where every satellite is in space. Now, a GPS receiver works kind of differently because it doesn't send signals. It only receives signals. So, and if you have at least 4 satellites sending signals to a receiver, it uses navigational equations inside the receiver to calculate your location. So in general, that's how GPS works. But now we're going to start talking about time. And I'm talking about very, very, very small time intervals. We're going to be talking about millionths of a second. Now, it's kind of hard to imagine a millionth of a second, right? So to help you out, assume for just a moment that a full second is 15 miles long, right? That's like from here to the airport, or from here almost to Delray Beach. If 1 second is 15 miles, a millionth of a second is less than an inch. That's how small we're talking about. So why do we need to know? Why are we talking in millionths of a second? Well, you remember when I said that the microwave travel time was exactly 1/10 of a second? What if it was off by a millionth of a second? If it was off by a millionth of a second, that distance would be off by more than 100 feet. And with all of your calculations, if you're trying to get your GPS accurate to within a foot, you can't handle 100-foot errors in all your measurements. So the way the GPS designers got around that is they equipped the GPS satellites and the ground stations with extremely precise atomic clocks. These clocks are so precise, they're accurate to within, say, 50 billionths of a second over the course of a day. So with that kind of accuracy, you can measure the distances to the precision that you need to make the system work. But see, that's where Einstein's theories come into play, because Einstein's theories affect the operation and the accuracy of those atomic clocks. And we're going to investigate how. First, we're going to talk about Einstein's special theory of relativity. He presented this theory in 1905, and it was one where probably birthed the most famous recognizable equation in the world, E equals mc squared. That's where energy of an object is equal to its mass multiplied by the speed of light squared. Well, much lesser known, but just as profound, he also had a little equation about time, and that the time can be changed, the time progression can be changed depending upon velocity. In this equation, velocity is u, and then again, c is the speed of light squared. But to get an impact of this equation, we're going to discuss a little twin paradox, okay? So imagine that you have two identical twins, and they're at an airport, and they have identically, perfectly operating, synchronized atomic watches, okay? Now, one of the twins gets on an airplane, and he starts flying overhead at 600 miles per hour. Ever so slightly, the watch of the twin that's on the airplane will be operating slowly compared to the watch of the twin on the ground. Now, that twin won't notice it because that twin is also aging more slowly at the same rate. So, but at 600 miles per hour, you really doesn't make much difference, because that twin in the airplane would have to fly a year continuously in order for his watch to be slower than the watch on the ground by 1/millionth of a second, because he's only going 600 miles per hour. But these satellites, the GPS satellites, they go 9,000 miles per hour. So it only takes like 3 hours for the clocks on the satellites to be slower by 1/millionth of a second than the clocks on the ground. So over the course of a day, they lose about 7 millionths of a second. And then we've already discussed how important those millionths of a second are. So next we're going to talk about Einstein's general theory of relativity. So once Einstein finished with the special theory, he was really perplexed at how to bring gravity and acceleration into his theories. And he worked hard. He worked with mathematicians. It was very complex mathematics. He had to have mathematicians actually invent some mathematics for him to be able to finish. And after 10 years, they were successful. Well, this is what the equations look like. I mean, really, really complex. But when Einstein solved those equations, he found out that massive objects like the Earth or the Sun that have lots of gravity actually distort space and time around their gravity fields. So when you apply this to the GPS satellites, instead of slowing down due to the velocity of 7 millionths per day, this would speed up the clocks on the satellites by 45 millionths of a second per day. So when you add those two together, you've got that normally 38 millionths of a second, these satellites would be running faster than the clocks on the ground. That is unacceptable for the calculations needed for the GPS. So what the engineers do is they take the clocks from the satellites before they launch them and they dial them back. So they're running 38 millionths of a second today slower, and that way by the time they get on orbit, they're running at the right speed. So that's how Einstein's theories are included to make the GPS system work. So now back to the sea turtles. This is a plot of the sea turtle nesting activity on this 9.5-mile piece of beach over the last 10 years. You can see generally it's going up. Not every year is the same because sometimes sea turtle species nest in off years and on years. Actually, we expect 2019 to potentially break a record, hopefully over 20,000 nests, because it seems like the peaks of the green nesting turtles and the loggerhead nesting seem to be peaking together this year. So I wouldn't be surprised if 2018 doesn't jump way over 20,000 this year. But considering that sea turtles take 25 to 30 years before they mature, you know, that little hatchling, it's not going to be nesting them for 25 or 30 years. Most of the improvement that you see on this graph happened because of actions that were taken 20, 30, 40 years ago. Specifically in 1973, the passage of the Endangered Species Act. So that was very important, and all that early work is paying off now, and the work that we're doing now hopefully will be paying off 20, 25 years from now. So what can we do? There's lots of things that we can do to help, right? If you're on the beach during nesting season, that's like from the beginning of March to the end of October. Don't leave any major holes on the beach. Don't leave lights on at night. Don't go out with flashlights to disturb the nesting. Minimize or eliminate, if you can, any single-use plastic. Plastic bags in the ocean are the worst because some of the species nest on jellyfish, and they look like jellyfish to the turtles. So, you know, there's still a lot of threats out there. There's red tide that's essentially polluting the sea turtle's food supply. So more needs to be done. But since most of this audience is middle school students, let me tell you the greatest impact that you can have. You're our next generation. You need to become the engineers or the chemist or the microbiologist or the public policy person or the environmental lawyer that helps keep this conservation effort going and make it stronger. So it's your job. We're depending upon you. Don't let us down. Thank you.